Welcome to our bridge design masterclass. Today we want to learn how to design this a single span 15-meter span single span bridge using Autodesk robot structural analysis software. Okay, so this is our bridge loading template. So you can see that we have the design life of the bridge to be 100 years. Then this is like a table of contents where we have the design data, deck loading arrangement, stringage and creep. Then we have the local wind effects. Then we have the computer analysis. We are going to analyze the slab traverse moment, deck institute, slab design, deck precast, slab design, transition slab design. Then we have the parapet to deck slab interface. Then the deck beam design, we are going to design the doctrinal precast beam, traverse beam, which is known as diaphragm beam, and shear interface between precast beam and the slab. So the substructure will only consist of abutment. It is actually a simply supported beam, beam that does not have piers. So there is no intermediate support. So it is abutment to abutment. Okay, so these are the code that we are going to deploy for this design, the HA plus 45 unit of HB loading. The HB load is actually an abnormal load which has 45 units, which has 45 units. Okay, so we are going to use the DD37 stroke 01 load for highway bridges, then BD52 the design of highway bridges parapet, then BD57 stroke 01 design for durability, then BS5 400 part 2 steel, concrete and composite bridges, then the BS8 110 part 1 and 2 structural use of concrete. So those are some of the combination, the load combination, the code combination that we are going to use for this very design. Then we will look at the partial factor for each of the element that we are going to consider for the dead load concrete, the at ultimate limit state. We are going to use 1.15. For the superimposed dead load at ultimate limit state, we are going to use 1.75. Then earth pressure, return field stroke surcharge 1.5, longitudinal load HA and associated primary load 1.25, longitudinal load HB and associated primary load 1.10. Then the live load in footwork, we are going to use 1.25. So this is just a very simple long bridge longitudinal geometry. So here we have the 15-meter span. Then we have the deck geometry, parameters, overall length of bridge 15, deck span length 15, total deck width 8 meter, width of carriageway 6 meter, width of walkways to cape 1 meter, then width of each lane 3 meter. Then we have the total numbers of 5 main girders, talking about the longitudinal beams. Then each of these beam is being spaced at a distance of 1.9 meter. Here we don't have overhang deck slab. Then we have the height of parapet to be 1.5. Then the approach slab, the length is 5 meter, the width is 6 meter. Then for the deck beam size, the thickness of the institute slab is 200. Then we have the thickness of precast slab 50. Then surfacing and overlay thickness 50. Parapet wall thickness 200. The walkway thickness, talking about the height of the walkway, is 350, which is also the height of the cape. Then approach slab thickness 300, then inner cape 250. Then for the main beam, the width of the main beam is 400 mm, the depth is 1000 millimeter. For the diaphragm beam, the width is 600, the depth is 900. So for the material property, we have already outlined them. So we move straight. So this is the detailed uh, traverse beam section where we define the overall width of the bridge to be 8 meter, then the carriageway to be 6 meter. And these are the different spacing, the, the beam spacing for the traverse section of the beam. Then these are the input parameters. So we move straight to the loading. This is the nominal loading. This for the slab, for the main beam, for the traverse beam. Then superimposed dead load we have for the surfacing, for the walkway, and for the K. So here this becomes this becomes this. Okay. So let's move quickly to the robot structural analysis provisional for the modeling of the bridge. Okay, so when you launch the robot structural analysis provisional software, the template that we are going to adopt is going to be shell design template. Shell design template. So if you open yours and it doesn't show this, you can come to new. So by the time you click on new, all the template will display and you'll be able to pick the one that is relevant to the bridge deck design. So we are picking shell design template for our design. Okay, so the first thing we do immediately after we open the robot structural analysis provisional interface, so we simply save the project. So let's quickly save this project. This is where I save my project. So I will say 15 meter span bridge tutorial. Let me use that tutorial. Okay, so I've done the saving. I've saved the project now. The next thing is to perform my setting. So to perform your setting, you click on tools, then you come to job preference. When you click on job preference, you start with the units. So for the dimension, our dimension is going to be the main structure the dimension is going to be in meter, then section dimension millimeter, section properties millimeter, then for diameter of reinforced bars millimeter, the reinforcement area is going to be in crack width this. So force is going to be kilonewton. Then for the stress we are using Newton per millimeter square. Newton per millimeter square. So click on Newton per millimeter square. Okay. So others for displacement we are using millimeter. Then for the force, our force is in Newton, kilonewton. Force is in kilonewton. Force is in kilonewton. So we click that. Then we come back to tools, click on job preference again. For the material, we select bridges. Then for the steel, select this for concrete. We're adopting grade 30 concrete. Then you click on modification to modify this. Click on steel. So the characteristic strength of steel is 410. That is what we have adopted. Then you select the strength of concrete and you click on OK. So basically for the design code for the load, for design code, the database, you click on vehicular load, yes, 5400. So we are okay. So we are good to go. Okay, so the next thing is for us to define the geometry of the bridge. The geometry of the bridge. So we are going to start with the x-axis. The x-axis is actually the traverse section of the bridge, which is this one, which is this. So we are going to define all these grid line. Now we are going to define this. Okay, so we are going to start with the parapet. We're going to start with the parapet. So here we insert 0 and click on this. Then 1. We're going to start with 0.2. This is where we got the 0.2 from. So from here to here is 0.2, which is the definition of the parapet wall. So you click on add. So when you click on add, the next one is for you to define the spacing of the main girders. The main girders spacing is at 1.9. 1.9. 1.9. So from here to here is 1.9, and we have 1, 2, 3, 4. So we have 4 of that distance. So we can now click on add. Then the last one is 0.2 to complete the overall width of the bridge. So we go back and you look at it. So add this 0.2. So we can now add. So what? As you can see, this is complete 8 meter. So we define the longitudinal length of the bridge. So that one is 15 meter. So we click on this, only one. So we add. So you can change the grid numbering to this. Then we apply. Then I will close. So this is the geometry of the bridge that we have defined. So we have our longitudinal length to be 15 meter, while we have the width here to be 8 meter. Now, so we want to define the boundary of the bridge so that it will enable us to insert our bridge slab. So to do that, you click on geometry, then you go to objects. From object, you click on polylines to contour. Now we are going to make use of polyline. So you click on polyline, and you click on that. You click on the first point, move to the second point, move to the third point, move to the fourth point, and then complete this. So you can close. So we have been able to define the boundary for the bridge, the boundary for the bridge. Okay, so the next thing that we will do now, I want to define the line for the parapet, the walkway, parapet, and the walkway. That is what I want to define next. So to achieve that, I will simply go back to geometry, go to objects, click on polish to contour. In this case, we are making use of line. We are making use of line. So I will define this, just define this line. I will close. Then I will come back, click on object, come here, click on line, then define this other line as well. So this is to help us when we want to insert our load. We will have a defined boundary to insert the load for the bridge. Okay. So now let's define other line. Let's define other line, which is this one and the walkway. So to define the 200, we can come to this, click on this. So when you click on this, it will highlight the line that you have already uh, provided. Then you come to edit, click on edit, come to move. From move, as you can see, this is X, Y, Z. So now we are going to offset this in the X direction. So in that case, we can insert 0.2 comma 0 comma 0. So meaning that Y axis and Z axis are all 0. So you now select, put the element number. The element number is 2. So you can click on execute. Okay. So I've done that. So I will come back again because the next one is 0.8. The element number here is 4. I will select 4, then click on execute. So I've done that. I've been able to define this and this. So I want to define this and this also. So I will come back. I can close. Then I have to look for this line. Then let me click on 3. That is it. Then when I click on 3, the line is being highlighted. Then I come to edit. Click on edit again. Come to this one. Now this one is going to be minus 0.2 because we are moving toward the left hand side, which is the negative. Then comma 0 comma 0. Then the element is 3. Then I will set the element number, which is 3. I will click on execute. Then I will change this again to 8. Then the element number here is 6. So I will click on 6. Click on 6. Click on execute. So I've been able to define the line for the parapet and the line for the walkway. So we can now close. Okay, so we can close. Okay, so the next thing we will do, we want to define the bridge deck. Now there are two ways that you can achieve this. You can click on the panel here, or you come to geometry. From geometry, you click on panel. From this panel, you can come here for the reinforcement. For the reinforcement, you can click on RC shell. Then for the slab thickness, you can come here. You click on bridge deck. Bridge deck slab. Then for the thickness, thickness is going to be 250. For global analysis, it's going to be 250. Why I'm saying that is because when you check out this, you see that we have the 200 mm thick for the institute concrete. Then we have the 50 mm thick for the precast slab. So for global analysis, we have to adopt 250. So now we have to select the grade of concrete to be 3037, 3037. Then what again do we have to select? We click on add, we close, click on add, we close. Then we can now and close. Okay, so we have done that. We have done that. So the next thing we will do is to define our load, to define the load. So for the load, we click here, we go to load, go to load, go to load. So we wait for the load dialog box to pop up. Now we have to look at loading on robots. We have to look at the type of load that we are going to have. So we are going to have the structural set weight. We are going to have the superimposed dead load. We will have surfacing. Then this is under dead load. Then under live load, we are going to have the HAUDL, the HKL push, the HKL, which is the knife edge load for position 1. This is a movable load. Then we will have it for position 2. Then we will have the pedestrian load. Then that is load for the pedestrian load for the walkway. We will have the HB load 45 unit for position 1. This is also a movable load. Then we have the HB 45 unit load for position 2. It is also a movable load. Now this particular one is for maximum. This one is for maximum span moment. We use this to investigate maximum span moment. While we use this one to investigate maximum maximum shear, maximum shear, maximum shear force, maximum shear force. Okay, so we will have the HB plus the HA plus the HB load. We have the H, that is for pairing 1 and then pairing 2. Then we will define the load combination. So let's start with the structural set weight. So for the structural set weight, you input structural set weight, structural safe, structural safe, set weight. So we can denote this by SW. Then we add. Okay, so the next load is the superimposed dead load. Superimposed dead load. Superimposed dead load. Superimposed dead load. SDL. So we add. Then followed by surfacing. Followed by surfacing. Followed by surfacing. So we add. So these are the three load that constitute dead load. So the next one is live load. The next one is live load. So in our list of live load, we have the HAUDL. So we define the HAUDL, 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 UDL we add. Then we have the next load is HACL position 1, the knife edge load position 1. So position 1, position 1, curl, curl 1. So we add, then we have curl 2, we add. Okay, so the next load that we are going to consider is going to be pedestrian load, pedestrian load, pedestrian load, pedestrian load, pedestrian load. So we can denote this by PD, by PD, PD, or PDL. Yes, yes, PDL. So we add, then followed by HB 45 unit position 1, HB, HB 45 units position 1. So HB 45 P1, P1. Then we have position 2. Okay. Then we have the HA plus HB loading pairing 1 and 2. So we have that. So this will be HA plus HB. We can pair it pair 1. So HA plus HB 1. So this we can do it for 2. Then this is 2. Okay. So we have done that. So the next thing we will do is for us to define each of these loads. So we are going to start with the superimposed dead load. Now for the structural dead load, the structural set weight is already inbuilt into the is an inbuilt load that we have in the software. So we don't need to calculate the set weight. So the software will calculate the set weight of the structure automatically. That's why we only define it, but we don't, um, we only list it out under the load, under the load cases, but we don't define the magnitude. So the software will define the magnitude automatically. So the next load that we will consider will be the superimposed lead load. So we look at our design template. So let's look at what constitute the superimposed lead load. So we have the surfacing, we have the walkway, we have the curb, and we have the parapet. So in this case, we want to start with the parapet. So the parapet, the parapet is per linear meter. The parapet is per linear meter. So let's this is out. Okay. So for the parapet, we have 7.5 kilonewton per meter. So we are going to define that. We are going to define that. So to define the magnitude of the load for the parapet, we select the superimposed dead load, and then we come to load definition. Under load definition, you click on surface. Under surface, you click on uniform planar load on contour. So you click on that. So we are going to define it under the Z axis. So this will be minus 7.5. Minus 7.5. Now, when you do that, you click on contour definition to define the parapet load. So I'll click here, click here, click here, click here, and click here. So the load has been defined. Then I will go back again to load definition, click on surface, come to this, click on contour definition to define the parapet load on this other side. So click here. Okay, so the parapet load for the left and the right has been defined. So we can close. Okay, then the next superimposed dead load is the walkway and the cape. Now, there are two ways we can achieve this. We can define the walkway load separately, and then we define the cape load separately. There are two ways you can do it. We can as well combine it. We can as well combine it. So what I want to do, I want to combine it. So when you combine it, you now have 8.505 kilonewton per meter. So we are going to apply this on the entire width of 0.8 meter, 0.8. So we are going to from here to here. As you can see, you see that this is the parapet and this is the width into in width of the walkway, which is about 722, while this one we have about this. Okay, so now we want to do that. We want to define that. So we come back to the load definition, come to surface, then under surface you have uniform planar load contour. So here we are going to define the walkway and the cape load, which is minus 8.505. 505. Then you click on that. Let's confirm. Okay, fine. Then we click on load definition and we define the load. We define this load. Okay, so we have defined that. We have defined the walkway load. Then we are going to do the same for this other side. So we do the same here. Okay, so we have defined that. We have defined that. We have defined that. So the next load that we want to define now will be the surfacing. We want to define the surfacing. Want to define the surfacing. So to define the surfacing is going to be applied on the entire width of the bridge, on the entire width. That is the carriageway, which is the 6 meter width of the the bridge. So to do that, we click on surfacing, then we come to this. Then the magnitude of that is 1.13. So let's confirm the magnitude of that load again. Okay, 1.13, and it is a square. It is an area load. It is an area load. So we click on contour definition, then we define the load here, 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 and here. So we can now look at it. Okay, so we can close. I think that is the oh, that I suppose I have selected the surfacing. So let's delete that load out. Let's delete it out. Let me let me just click on this. Let me click on this. So let's delete. Okay, so I've deleted it out now. So let me select the surfacing. Okay, so let me select the surfacing. So under surfacing, we can now define it. Can now define. Okay, so here we click on this, click on this, click on this, click on this. Okay, so that is the surfacing. So we can close. Okay, the next load that we are going to define is going to be the HA load. The HA load. So we select the HA load, and the HA load is going to be defined as a notional load. This is the HA load. It's going to be defined per notional length. It's going to be defined per notional length. Now, this is the HA load when it was not, when the length factor has not been applied. This is the HAUDF for the 15 meter span is this one. Now, load on each span without application of the length factor is this one. But when the length factor is being applied, so the load now reduced to 15.00 kilonewton per linear meter. So for us to apply this load, we have to define the notional length. Now, in our calculation template, we have already done that. We have done that. This is the numbers of notional length for 6 meter width. is this. Now, when you look at this, it's a carriageway width of 5 meters or more. National length shall be taken to be not less than 2.5 meter width, where the numbers of national length exceed 2. Their individual width should not be more than 3.65. So already they have defined they have given us a condition for the establishment of the notional length, that the notional length width should not be more than 3.65. So the carriageway shall be divided into an integral numbers of notional length having equal width as follow. So carriageway width in meter, the notional length. Now from 5 meter up to and including 7.5, we have two notional lengths. So the width of the carriageway here is 6 meter. So it falls under the first condition. So under this condition, the numbers of notional length is 2. So that is why we have this these two. Notional length width for 6 meter is we divide it by 2. So when you divide this by 2, you will have 3 meter. And you can see that it is within the 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 definition, the width definition that the code has recommended for individual widths of the notional length. So we have our own, we have 3 meter. We have 3 meter. So here we are going to divide this by 3. So that our notional length is 2 number and is 2 and each width of it is 3 meter. So let's go to the and the notional length will start from the edge of the walkway. So let's go back to geometry. From geometry, I want to check out this. Okay, let me remove. Okay, so from geometry object 8, so we can define our notional length. So you come to edit, click on edit, come to copy. This is x, so it's going to be 3 meter, comma 0, comma 0. It's going to be 3 meter. So I will click on the element definition, which is 8, and then click on execute. Okay, so the notional length has been defined. So we can go ahead and apply the HAUDL. So from our analysis here, the HLUDL is actually 15.00 kilonewton. 15.00 kilonewton. So let's come here, click on load definition, come to surfacing, click on this. Then under this we have -15. Then we click on contour definition. So we are going to apply this load on each notional length. So we will apply on this one first. Okay. Then we apply on the second one. Okay, so we have successfully applied our HAUDL load, so we can close. So the next load that we will apply will be the HA that is the knife edge load, and this one will also be applied on each national legs. It will be applied at the center of the the bridge, the center of the bridge. Okay, the knife edge length is a linear load, it's a line load. So to achieve that, we will do it first for position one. Then after that, we move to position two. So for position one is for the maximum bending moment. Then position two is for the maximum shape. So let's start with position one. So we click on this. Then we come to the load definition. We, we click on this. Then we come to linear load to P. Linear load to P. So we are going to consider this. So let's look at the knife edge load. This is the knife edge load. When we apply the length factor, but when the length factor is not being applied, we have it as 40 kilonewton per meter. But when the length factor is being applied, we have it as 32.9. So this is the length factor that we apply. Okay, so 32.9, and it is, you have seen that it is like a line load, a point load. Okay, so we minus 32.9, minus 32.9, and it's going to be at the center. It's going to be at the center. So you can now apply. Okay, so that has been applied. Then we go back again, so we can apply on the second position. So this, okay, so we can add, and from there we can close. Okay, so this is for position one. This is for position one. Then for position two, we are going to apply it at 0.005 from the edge, 0.05. So we can actually copy this. We can copy this. We can copy this. This is the load. So we come here. We can copy this. Come here. We paste. Okay. So when we paste, we come here. We click on position two. Then we come here. We change this to position two. We change this to position two. Okay. So position two. I can as well copy this again and then paste here. Now I'm copying this and then paste it here. So here this is this, then I can change this. Let me change this to position 2. Okay. Okay, so now let me switch this to position 2. This is position 2 also. Okay, let me do something here. Let me delete this and also delete this, so I can copy this and copy this. Okay, so let me change this to position 2. Then I will come here, change this. I want to change this to position 2. Then change this to position 2 also. Okay, so what we need to do is we want to change the position. Remember that position 1 is at the midspan. Then position 2 would be for maximum share, would be at 0.5 away from the edge. So I will come here. I'll come here where we have 7.5. So we change this to 0.05. Change that to 0.05. Then come to this one. Change this one also 0.05. Then for this one, so we change this 0.05. 0.05. Okay, so we have successfully done that. We have successfully done that. Okay, so we have put the we have we have we have defined the HA load position 2 and position 1. Okay, so the next load that we want to define right now is pedestrian load. The pedestrian load. So we change this to pedestrian load. Now, for the code says that for a length between 0 to 36 meter, so we are going to adopt 5 kilonewton, 5 kilonewton, 5 kilonewton, the 5 kilonewton per meter squared load, talking about the pedestrian walkway between 0 to 36 meter. So when you check the longitudinal length of our bridge is just 15 meters, so it's fall within the recommended load. So we come to this. So the live load on the walkway is going to be defined from here to here. Okay, so we click on load definition, come to surface, come to uniform planar load, then we change this to -5, -5. Then you click on contour definition. So you define the walkway load. Okay, so you click on the second one, click on contour definition, click on this, click on this, click on this, click on this, click on this. Okay, so the pedestrian load has been defined. Okay, so you can close. So the next load that we want to define, which is the most important load, is going to be the HB 45 unit load. And we are going to define it at position 1, and we'll also define it at position 2. So this is the most important load. This is the abnormal vehicle load, and we have to be very careful when we apply it on the bridge deck. So let's start the application of this load. Now the HB 45 unit load is actually the an axle load that is multiplied by 10 to give us 450 kilonewton, and that is divided by 4, which is an axle is made up of 4 wheels. So we are going to divide this by 4, which will give us 112.5 for each of these. Now let me show you how this load will be applied. Let me check my document. Let me check my document and see how this um, let me check my document. Okay, so this load is going to be defined in this format. It's going to be defined in this format. So we are going to have at this point define the load, then we space it at 1 meter for each for the national length that we are going to consider. And the most onerous position would be at this arrangement, positioning of HB load to produce desired effect. This is what will produce um, the maximum span moment. So meaning that this last wheel of the load, the last wheel of the last this second to the last wheel of the load must be at this 1.5 meter away from the center of the bridge, away from the center line of the bridge. This blue line is the center line of the bridge. So for you to have the most desired effect, so it means that this wheel, this particular wheel, will be placed at this point. So we are going to demonstrate this. So the first thing we will do is to establish the center line. Then when we establish the center line, we will position the wheel, then we move it to the most onerous position. Okay, so let's establish that. So I'm gonna establish the center line first. So I go back to geometry, then come to objects, click on line, then define the line. Okay, I'll close. So when I define this line, the next thing I'm going to define will be I'm going to define a node. So I click here. So I click on this point. Okay. So that is a node. That node has been defined. So we are going to apply the load from the node. So that is the node that has been defined. So let me go back to the load. So let's look at this. Okay, so we come to HB position 1. Okay, so I'll click on that. So when I click on that, I'll click on load definition. Remember that this is the load that we are going to apply. This is the HB load 45 units. So when you now multiply by this, then you have 450, and per wheel will now 4 wheels make up an axle. 4 wheel make up an axle. So in order for us to distribute the load on each wheel, so we have to divide it by 4 to give us 112.5 kilonewton. Okay, so I'll go back here. I'll click on another force. Okay, then here I will insert minus 112.5, minus 112.5. So I will click on add. When I click on add, I will click on apply. So it has applied it. Then let me activate the load value description. So you can see that this is the load value description. So now, according to this arrangement, I've just established that load at the center here. So I want to duplicate it. That will be 1, 2, 3, 4. So I achieve that. For me to achieve that, I will I will close this, then come to geometry. No, go to edit, click on edit again, then click on copy, this will be at x axis. So I will click on 1 comma 0 comma this is going to be 3. Click on 3, click on execute. Okay, so we have gotten that now. So I can close. Now I want to this is the center of the the bridge. This is the center of the bridge. This one. So what I will do, I will position it at the most critical position to give us the desired effect. So what I will do, I will just offset I will copy the load 1.5 from this 1.5, then I will have one. Okay, this is what I will do. This is what I'm going to do. So let me offset 3 meter, which is from here to here is 1.5, then from here to here is 1.5, then here is 1.8. Then I'll do the same thing for this side. Then after that, I will now move to give us the most desired effect. So let's quickly do that. Okay, so to achieve this, I will go back to edit, go back to edit, click on edit, go to copy. This is on the y-axis, so this place here will be 0, 0. This will be minus 1 point, minus 3. Let's check out then 0. Let's check it out if it's gonna give us that. Oh, okay, let me, okay, so let me copy everything. Let me copy everything. Okay, I think I've copied everything now. So I can now move. Okay, so 3 meter. Then the next one will be 1.8 minus 1.8. That will execute. Okay, that is fine. Okay, so I have gotten that now. I can close and let me just turn this so that I can copy this one. I can just copy this. Let me turn off this. So let's copy this. Okay, so we come to edit, click on move or copy. Then this will be on the positive y direction. So this will be 0, comma 3, comma 0. So let me execute. Okay, then the next one is 1.8. Have I done that? No. So I need to copy this. I need to copy this again. Need to copy this again. Okay. Come here. Click. Click here. Then 0, 1.80. Okay. So I've done that now. So I can now go back. Okay. So now before we effect those, before we now place the load on the most onerous position, what we need to do right now is that let's go back to this. Now you see here we said that the wheel must be 500 meter away from the walkway. This wheel load must be 500 millimeter, sorry, 500 millimeter away from the walkway. So we are going to move the wheel load 500 away from the walkway. So let's demonstrate that now. Demonstrate that now. So let me highlight everything. Okay, I can come. Let me go to geometry. At geometry. So let me click on the note, all the notes. To achieve this, click on one, then press shift, click on the other. Okay, fine. So let me move this by one by 0.5 meter the away from the walkway. So to do that, I will just simply come to edit, come to move, click on move. This will be left hand side 0.5 comma 0 comma 0. Then I will click on move. I will click on execute. Okay, so you can see that it has been moved 500 millimeter away from this. Okay, so I can close. I can now close. Okay, then let's go back to the load and go back to the load so you can now see that the load has been moved from this 500 away from this thing. So now for us to get the most onerous position of the wheel load, so what we need to do right now is we need to move this by 1.5. So this particular wheel must coincide with this 1.5 away from the center line of the bridge. 1.5 away from the center line of the bridge. So that is what we want to demonstrate now. So I will define that 1.5. I will define the 1.5. Define the 1.5. So I will go back here. Go back. Click on geometry. On geometry. Then let me define these objects. Okay. So this is on y-axis. So I'll come here, click on edit, click here. This is y. This should be y negative. So 0, comma, minus 1.5, comma, 0. So I will copy. Okay. So it has now copied it to 1.5. I've copied the one. I've defined the 1.5. So this is what I'm going to do right now. This is what I'm going to do. So let's go back. Let's go back there. Let's go back there. So I'm going to move this load. I'm going to move this load from this point to this point for us to have the desired effects. That is what this. That is what positioning of the HB load to produce desired effect mean. So we are moving this to this position now. So let's do that. Let's achieve that now. So I will click on the load. Okay, let me go back. Let me come to geometry. Come to geometry. Then click on this node. And then click on this. Fine. So that has been defined. So I can come to this now. Can come back to load. Can come back to my load. Okay, let me stay here. Let me stay here and do that. Let me stay here and do that. Okay, so what I will do right now, I will move this to this position, move this to this position. So I'll click on edit, click on move. So I'm moving it in the positive direction. I'm moving it in the positive direction. So what I will do, I will click here, then come to this point, move. Okay, fine. So that load has been moved to that position now. Okay, so we can close and let's look at it. That is perfect. That is perfect. That is perfect. So we can now delete this other load. So we can delete this out. We can delete this load out. We can delete this, delete this, delete this, delete this. Okay, that is fantastic. So we have been able to achieve the HB load at position 1. So you can now see that we have been able to achieve that at position 1. This is the positioning of the HB load to give us the desired effect. Now, this very position is used to investigate the maximum span moment. Maximum span moment. What we have just finished doing is to investigate the maximum span moment. So we are going to do the second one to investigate the maximum sub shear force. Okay, so let's quickly do that before we can come to the conclusion of this video. Okay, so to demonstrate this, what we will do, we are going to let's okay. So the HB load, as you can see, this is 6 to 20, 6 to 21. So we are going to copy this. We're going to copy this, position it here, paste. Okay, so we can change this now to position 2, HB position 2. Fine, that is position 2. Okay, so from this position 2, so we can select this position 2, So when we select position 2, so let's copy this. So we have to take note of what we are copying. We have to take note of what we are copying. So we are copying this. Okay, which is 14 to 21. 14 to 21. 14 to 20, 14 to 21. The first one was 6 to 21. The first one was 6. Okay, so we are going to copy this. So we click on this. This is position 2. Position 2. So we are going to copy, edit, copy. This will be on the negative Okay, this we might not really. So we click on this and we pick it to this point. So this is 22 to 36. 22 to 36. 22 to 36 for the 22 to 36. Okay. So we change this 22 to 36. Okay. So for position 2, for position 2, 22 to 36, then let's look at position 1. Let's look at position 1. Okay, position 1 will be, let's get this. Position 1 will be 6 to 21. 6 to 21. Okay, so I think we are good to go. 6 to, this is what we had in the first one. This is what we had in the first one. So I think we are good to go now. This is what we had in the first one for position 1. Then for position 2, exactly. So this one is used to investigate the maximum shear force, while position 1 is used to investigate the maximum span. So we are going to end the video here. I believe that you have learned a lot from this model. So thank you very much for your attention. So see you in our next model. Bye.